to thank the coordinators of this FDP, Professor Jagannath Rai and Professor Ramesh Babu from Professor Jagannath Rai from NITW Warangal and Professor Ramesh Babu from this SR University for their kind invitation to deliver my thoughts here. As you know that this FDP is all about this data science and business analytics. So today I am going to actually deliver my talks particularly on this clustering techniques, and we will see that how these clustering techniques can help us for this business analytics purpose. I'll share my PPT. So I hope my slides is visible. So Jagannath sir, can you confirm it? Is it visible?
Yes, sir, yes, sir, visible, sir.
Okay.
Very good.
Yeah. So thank you. So once again, I would like to request my participants so that during my session, if you feel that slides are not moving as well as I am not audible clearly, then please contact with your coordinators so that they can immediately contact with me, since all about it's online session. So maybe technical problems we cannot avoid sometimes. So anyway, so I will take care. If in case of any issues, you will contact with your coordinators so that coordinators can immediately get with me and I can try my best to resolve the issues. Now, this is my presentation outline today. So whatever we are going to discuss today, and clustering fundamentals initially discussed, then K-means clustering, then fuzzy C-means clustering. We'll try to find out that how we can associate clustering with these optimization techniques to get some fruitful result, and then we'll show some experimentation, whatever we have done, then we'll come to conclusion. Now, so let us start that. Yeah. So what is clustering? So I think once we telling regarding clustering, so we should say that obviously that clustering has a very good relation with this data science or big data. And yesterday also I was telling that we have actually a huge amount of data, and in every 6 months, simply whatever data we have with us, simply that is getting double. So that is becoming double whatever data we are having in every 6 months. Now you can assume that how much amount of data I think is stored day by day basis. So what you will do with this data? So obviously, if we can find out if we can extract some meaningful and some tangible information from those collected data, then probably we can do some good business, or we can contribute something in the context of business analytics. Actually, this is our main goal for this data mining. Okay, so once we have some high volume data, then we need to extract some meaningful and some tangible, that means meaningful, and some obviously real informations we want to extract from this collected data. Now, since we are having some high volume data, as you know that sometimes data may be structured, sometimes data may not be structured. So really, it is very much difficult. And as well as, sometimes whatever data we are working or we are processing, data may be labeled data, sometimes data may be unlabeled data. So, so in these cases, then how it is possible so that we will extract the hidden patterns or extract some meaningful values from those data? We will see how to do that. So now, as I was discussing that, as I told, that data may be in various form, and obviously once data is in unlabeled form, it may be labeled data, or it may be sometimes it may be unlabeled data. Okay, so once it is unlabeled data, then how we can perfectly organize, okay, how we can perfectly categorize this unlabeled data. Okay, so once we are working with this unlabeled data, and particularly in the context of data mining, obviously we can do this thing using this cluster analysis, whatever is our topic of discussion today. So we are working on this data mining. That means we have some high volume data where our major target is that we want to fetch, we want to extract the meaningful data. So at the same time, we are finding that whatever data informations we have, all those belongs to this unlabeled category. Okay, once it is unlabeled category, so then our primary objective or primary task will be to do some organizations of the data, to do some proper categorization of the data, so that maybe which are similar kind of data, maybe they will come into one place, and which are another different types of they will move to the different place. Oh, so that is the data clustering, what I was trying. So the meaningful grouping of this unlabeled data that we say normally as data clustering. Okay, so as I told that what is the goal of this data clustering, so that we'll combine, we'll group together similar kinds of data in another group and these similar kinds of data in another group, like that we want to proceed actually. Now, so once we want to categorize that similar data into one group, then you may assume then what will be the output here. Obviously, then it higher this inter-cluster distance will be less. That means inter-cluster similarity will be much more higher. And obviously, it will lead to lower inter-cluster similarity. Intra means it is inside clusters. Inter means it is among various clusters. So obviously, once we group similar kind of data, or since it is unlabeled data, so we cannot do that much things with this unlabeled data. What we can do based on the features, so simply we can put together the similar kinds of data in one place. So that our objective is here, once we will put together this similar kind of data in one place, obviously that will lead to this intra-cluster distance. So intra-cluster distance will be minimum. Intra-cluster distance minimum means it will lead to higher intra-cluster similarity and obviously lower inter-cluster similarity. Now see here I want to show you some examples here. Now see, so how we are grouping. So we can say this is one cluster, okay, this is another cluster, like that. This is our one cluster, this is our another cluster. Now here simply I think often I am telling one point that okay, now similar kind of data we want to put together, similar kind of items we want to put together. Now how we will find out mathematically that which is similar items? Okay, how your algorithm will find out which is similar items actually. So to find out similar items here, we are actually computing some distance measurements we are applying. So here we are applying this Euclidean distance measurement. So that means, suppose I am taking a center, assume. So this is my cluster, okay, this is my cluster, and this is my cluster center. So if I find out the distance from the cluster center to all these objects, okay, and if we take the summation, then we will find out here the distance that is called intra-cluster, here distance will be less only. Now see here, so whatever I'm telling, so that means again this is the cluster. So here I'm finding this is my cluster center. So if I find out the distance, so that means once distance is less, what does it mean? Obviously distance less means similarity will be more, and distance more, that means similarity will be less. Now see that, so from this cluster center, if I take distance of this, distance is more. If I take from this cluster center, distance of this object, if I consider distance of this object, if I consider distance of this object, then see, distance of all these objects from this particular cluster center, let us say this is E, this is A, this is B. So distance of all these objects from this cluster center are more in comparison with these particular objects. That means obviously here, this particular objects we may put together. We can say that, okay, these are much more similar comparative with this other set of objects. Now, what is the real life example of this clustering? See, in image segmentation, you will find out a huge application of this clustering technique. Now see, so simply here some grass field is there, maybe some road is there, maybe some water is there. So how will differentiate which is the water body? Okay, which is the road? the grass fields. So each and every place, perhaps, so once maybe you are driving through your car or something, then again, if you go through this GPS navigation system, again it will show you that you will get to know that, okay, when you will find out, okay, that something, maybe some park where more green trees are there, then I think it will put together in a different manner. So that means ultimately, so if some lands are given to us and you need to find out, okay, that what kind of objects are there in the land. Some water body may be there, some roads may be there, some grass fields may be there. Now, if you do the clustering techniques, so you may not understand that, okay, what is the water body? Okay, because this is unlabeled data only. What is the that particular road? What is that particular grass fields? But ultimately, it will do the categorization. Grass field will be separated from water body, or whatever you road, that will be separated also from this grass field as well as from this water body. Obviously, that will help us to take some decision. Now, as I told that, what do you mean by cluster analysis? So as I told earlier also, that similar kind of data are related. So to one another, we'll put within the same groups. Now, which is dissimilar or unrelated, so that is another groups. That means simply our objective is to put together the similar types of data based on the feature vectors into another group, into one group actually. Okay. Now, as I told that for clustering, as you know, that two kinds of learnings are there. One is supervised learning. Second one is this unsupervised learning. Now, in case of unsupervised learning, so as you know, there is no predefined class actually. Okay, no predefined class. So you know that learning by observations, learning by examples, so that belongs to the supervised category. Where label data is there, you know which item is meant for what. But in case of unsupervised learning, you know, no predefined classes. Okay, so that if this is your features, if this is your attributes, you don't know what is your target attribute. But in case of supervised learning, what I told you last day, some classifications I was trying to show Bayesian classifier. So where I clearly told I took some set of attributes, and and among those set of attributes, some set of attributes belongs to the feature vector, other belongs to the class variable. That means they are based on this features or set of attribute. Clearly, it was given if these are the attribute values, then this is the classification. If these are the attribute values, then that is the classification. Everything is given there actually. But that means predefined classes are there. If attribute values are this, then that may be the predefined classes. But in case of unsupervised learning, there is no predefined classes. That is the main problematic here. You have some feature values, you have some attribute values, but you don't have any predefined classes. Then what you will do with this? Then only the thing that you can do, that you can put together where where the features are similar, you can put together in one place. That is the clustering only. And you know, this clustering, typical applications I can tell, pre-processing step for many other algorithms. So today, whatever experimentation I will show maybe in the last half an hour, so there you will find out that clustering techniques we are using to find out the actually initial candidate solution or initial set of population for gravitational search algorithm. So normally it is used as a pre-processing tools for various algorithms, and today also we have used this as a pre-processing tool for some of our optimization techniques. Again, you can use simply a standalone unit actually for this data visualization or data distribution. Sometimes it does a data visualization or data distribution in the context of this business analytics or data science is very much important. So later I will show you that why these things are very much important in the context of this business analytics. Now, before proceeding, once again, let us little bit to recap that supervised learning and unsupervised learning, because whatever the content today we are discussing, all this belongs to this unsupervised learning only. As you know, that supervised learning means, so in the last session already I told, discover patterns in the data that relate data attributes with the target attribute. That means we have some data attribute. So based on the data attribute, so we can tell, okay, if this is the data attributes, then that will be our target attribute. So target is given. target attribute is given. Okay, so target attribute, that means target class. Target class is available for the set of the given attributes actually. So then if you have those set of data where you have the target class for a set of attributes, obviously, then you can train your model, okay, with those attributes and the class attributes, and then easily you can predict once some set of new attributes will be given to you. So from in which class it will belong, that easily you can predict from that. That I have written here, these patterns are then utilized to predict the values of the target attributes in future data instances. Now, what is unsupervised learning? You see that these data have no target attribute. Whatever clustering we are discussing, so we have only the features. So we don't have, okay, that if these are the features that belongs to this class or this category. So that kind of information we don't have actually in case of unsupervised learning and clustering, as you know, that one type of unsupervised learning. So what we can do, obviously here, we can analyze the data, okay, for our business purpose. We want to explore the data to find some intrinsic or hidden structures or hidden characteristics or hidden values inside this data. So obviously that may be helpful to take some decisions or to do some other work actually. So since we are dealing with mainly clustering, so better to focus on this unsupervised learning process only. No, so it has, as I was telling, that here, whatever data points we have given, this is unlabeled data point. That means we don't know actually, okay, that no label that which class it may belongs or whatever it may be the category, we don't know anything. So these are unlabeled data point only. There is no mapping. Okay, if this is the data points, then what will be the class? So that kind of mappings are not there. So then we need to find the patterns or a structure in the data. So this is the main goal for any clustering algorithms. So see, clustering, that will automatically group the data points or items, okay, into similar or related group. Okay, now I hope that now you are getting some ideas regarding clustering, whatever the point we are going to discussing. Now maybe you are thinking that what are the main challenges of this clustering? First of that is how to measure the similarity. Actually, sometimes data may be the high dimension data, number of features may be involved, and sometimes, that whatever the data you are clustering, that may be unstructured data. That means different data may have some different features. In this case, where set of features are not similar, so in this case, again, I am asking you, okay, to divide these data items into 3 or 4 clusters. Now see here, then what you will do actually. So actually, as I told earlier, that similarity measurements is very much important for us in case of this clustering technique, similarity measures. Now once itself few data items belonging to different domains actually, so maybe their units are different, then how will measure the similarity? How will measure the distance? So obviously that is a very much crucial problem for this kind of clustering techniques. But again, I should say that many researchers contributed to this domain so that it can be very much simple. Again, another thing is that, so how to define what should be the ideal number of clusters? Number of clusters, I mean to say. I am giving you some set of unstructured data, unlabeled data, and from that, you want to find out the clusters. That means you want to group similar kind of data in one place. But in case, that if I don't say what will be the number of clusters, or if I predefine this is the number of clusters, then how your algorithm, if I say, okay, so this set of data, unlabeled data, you put in 5 clusters. Maybe here 5 clusters is not that much enough. It may be less. Sometimes 5 clusters may be more. Now see, if I predefined the number of clusters in case of clustering analysis, so that is also a difficulty actually. I don't know that if I predefined, okay, if we need to cluster all these data items into 5 groups, and where mostly data items can be fitted into 3 groups, then how to convert them into 5 groups? It is a very difficult kind of situation. So this is the main challenges of this clustering algorithm. Whatever clustering algorithm we will study today, so we will prefix actually. We will prefix, okay, that will be your number of clusters. Now see the challenging situation. how we can prefix the number of cluster actually. It is very difficult to prefix the number of clusters. Or what will be the ideal number of clustering? Can you determine the number of clustering? What will be the number of cluster dynamically? So anyway, so there is some techniques also how we can determine the number of clusters dynamically also. But today to make this session much more easier, so we'll focus particularly on a clustering technique that is known as K-means clustering, where number of clusters are fixed, number of cluster will be K. So that is the problem that with this mainly clustering techniques. Now you see, so this is the various example of this clustering. Okay, where each and every places, where not each and every places we can apply this concept of clustering. This land use, so how much important it is. So if it will identify similar kind of land, okay, similar type of land, okay, in our earth. So once land are similar type, so that will group. Suppose some big industry or something that one are finding some land actually, okay, so they want to install their factory in some of the lands. Then based on the land nature actually, okay, that okay, if we apply clustering techniques in a particular area, then it will be okay, these are the vacated lands, no use lands. That means it will be in one category. So therefore, them it may be helpful to identify or to locate the land. So where without damaging or without affecting too much to a society, they can install their industry. So like that in marketing, if I say what is the application of clustering in marketing, so probably you'll be wondering. And one of the main system in marketing that is particularly used in business, that is called recommender system. So that is another research area actually, recommendation. So suppose one shopping mall today they are finding, because they are storing all these their customer data, what they are purchasing, what time they are purchasing, how much amount they are purchasing. So all these things are stored in their database. So suppose based on that, they are finding, okay, so majority of my customers, okay, those who are purchasing product A, B, and C, they are purchasing product D also. But what happened? Product A, B, and C, I have grouped in one place, but product D maybe in second floor. So then what they do? Okay, then to make easier for customers, they will bring product D in, I think, in the same line or same row where they are keeping product A, B, and C actually. So again, what they will find out? Okay, once they are finding few customers, once they are purchasing product A, B, C, and D, so maybe they showed their interest to purchase product T also, and where product T may be little bit costly. Then what they will do? Then they may apply it for the sales, for the business purpose. They may apply little bit. I think what I should say that something discount, some discount they may give on this another product to attract more customers. Okay, because ultimately, if maximum number of customers purchase that product, it will lead to them some profit only. So see how business is coming into picture once we're applying this clustering analysis. They need to identify now that what kind of products customers are preferring. So better to put all those products where the customers are preferring into one place to make it convenient for the customers actually. And another important thing is that city planning. City planning. So once you want to plan for a city, big city, then what you need to plan? Okay, that in some which area? Okay, let us say, suppose in Warangal we want to make it a green city. That means we want to make it a smart city. That means here we need to do the clustering. Okay, we need to find out what type of houses are there in which place. Okay, we will find out, okay, in this place majority of houses are this, or in this place we are finding that some pollutions are coming from this particular place. That means here maybe houses maybe are of type something industry or something else. Okay, that means they are doing some other works maybe going on there. So here easily we can category actually that which place, what kind of houses are there. Okay, so that may be helpful for our city planning. And earthquake studies similarly we are getting climate, economic, how we can plan, so we can how all these sectors can be benefited using this clustering technique. Here I have shown you a very clear example that Maybe it may be misleading that, okay, yesterday I told Bayesian classifier, that is classification techniques, and today we are discussing clustering. So to avoid any confusion between this classification and clustering, so I have come up with this thing. Now see, so this is our cluster boundary. Whatever I have given, this is our cluster boundary. And this straight line I have drawn. So this is our classification boundary actually. If this is your classification boundary, then I may say this is our class 1, this is our class 2. See, if I draw this classification boundary, then enter these items will belongs to my class 1, these items will belongs to the class 2. But in case of clustering, it is different. Clustering, so this is my actually cluster boundary. Okay, so that means here I am finding these items are similar, and here this side I am finding items are similar. Now here simply definition, if you want to find out clustering and classification, see, in clustering data points have no labels. So once data points have no labels, then how you know this is class A, this is class B, or this is class C? Can you find it out? Or this is class 1 or this is class 2? We cannot have any, we cannot do any conclusions actually. So simply we can differentiate the data items which are similar from the data items which are dissimilar. So clustering data points have no labels, but in classification, see, most data points have labels. Since here in this classification, the data points are having labels only now, that we can tell, okay, this belongs to class 1, this belongs to class 2, or some other data points belongs to class 3. Only for that we can tell that. Now, another important measure that, okay, that how to find out, okay, that what is a good clustering actually. How to check that which clustering is good, you know. So good clustering, so it will produce high intra-class similarity, cohesiveness with these clusters. That means whatever the various objects that may be very much closer to the centroids. Centroid means here I mean to say this is the cluster center. High intra-class similarity, cohesiveness with the clusters. That means which are the similar data points or data objects that may be very much closer to the cluster center. Second one is low inter-cluster similarity. Obviously, inter-cluster similarity should be less only. Distinctive between the clusters, we can differentiate, we can make a difference between each and every cluster here. So we can tell the quality of the clustering method depends on this similarity measure actually. So it is similarity measure, whatever similarity measure you are using. So based on the similarity measure only now we can compute or we can determine the quality of a cluster. Now this is our motivations for behind clustering. Obviously the main motivation is understanding the data better. So first thing is that we need to understand whatever data day by day data you are storing. Okay, so we want to analyze, we want to visualize the data, we want to use it for business perspective. See, one statement I have written here. Segment the market or customers of a service. So see, this is purely business only. So we want to do some segmentation on the customers. Okay. So like that means, so if some shopping mall, if they find, okay, that mostly customers are coming at 8 o'clock. Suppose their closing time is 8:30. They will find, no, some customers who are purchasing more, they are coming at 8 o'clock. They have noted it. Okay, and which products, items they are purchasing there, they have also noted. Then what they will do? Obviously, that means which products they are purchasing. So maybe they will apply some discount on this product, and they so to attract majority of the customers. So a clustering analysis also you can use as a precursor from some other applications. So maybe recommendation systems or maybe text summarization or data compression, some other purpose. So let us come that some categories of this clustering. Now, right now we have gathered some ideas on this clustering, some context of this clustering, benefit, and how it can be used for the purpose of beneficial of our business. So few things we have got. Now let us make some categories on this clustering technique. See, mainly two categories we can do. One is hierarchical, second one is partitional. Okay, I'll tell. In case of hierarchy, so this is linkage based, but partitional it is not linkage based. So once I'll proceed, it will be much more clear. This is agglomerative, this is divisive. So this is two types. So maybe you are right now, maybe you are not understanding. Anyway, once I'll proceed, you will get it. See, here I have given all the explanation, different type of clustering, partitional. Partitional means what? Different set of items into non-overlapping subsets. Each item will be member of one subset. So once we are doing the clustering here, partitional means we mean to say that one item should not belongs to two cluster. One item will belongs to only one cluster. There will not be no overlapping of the clusters. Okay, clusters will be entirely different. So overlapping of the cluster means suppose these items are there in this cluster, okay, and this is another cluster, just check. So here it is overlapping is there. So this is another cluster. That means here I mean to say here it is overlapping is there. That means this plus that belongs to these two clusters as well as small circles. This is my data points that also belongs to this cluster. So that kind of overlapping is not expected in case of this partitioning clustering. Each item will be member of only one subset. What is overlapping? So in case of overlapping clustering, so one data item may be belonging to two different cluster also. Now, you know that sometimes what we find it very difficult, that it may be one item, it is very much difficult to put in some clusters actually. So one item may be very much close to multiple number of clusters, then what we will do? Then you cannot avoid it. Then we need to put the same item into multiple number of clusters. Actually, that is another kind of clustering technique. So once I will proceed, then obviously we will discuss that kind of clustering technique. Now, this is fuzzy clustering. As I was telling right now, that sometimes there might be the situation, it will be very much where it will be very much difficult to differentiate that, okay, that this cluster, this object belongs to a first cluster or that object belongs to second cluster. That means possibility or probability is there that one data point or one object may belongs to multiple number of clusters. Then how you will solve that kind of scenario actually? You cannot avoid that because situation is like that sometimes, possibility is like that you cannot differentiate, okay, each and every item should belongs to only one and only one cluster. Some items may be belonging to multiple number of clusters also. There we need to use this concept of fuzzy clustering. So what is fuzzy clustering? Here we will focus more. I have few slides on this fuzzy clustering. Now here, as I was telling that fuzzy clustering, what does it mean? So, so once I will say that some items belongs to some cluster, absolutely belongs to some cluster, then we will make the fuzzy membership grade as 1. Once it does not belong to the cluster, it is 0. Okay, but what is the possibility here? As I was telling, that one item may belongs to multiple number of clusters. Obviously, multiple number of clusters with multiple membership grades. Okay, so maybe suppose I'm telling, so this is one of my item. Okay, these are the clusters. This is one cluster. Let us say these are the clusters. Okay, that means the possibility is there that item may belongs to this cluster, that item may belongs to this cluster as well as this cluster. Let us say that belongingness of this item to this cluster, I can tell it is 0.3. Let us say I'm telling 0.3. Degree of belongingness of this item to this cluster, I am writing 0.4. That means degree of belongingness means what I mean to say that contribution of these items to this cluster is 0.4. Contribution of this item to this cluster is 0.3. Suppose here I am writing 0.2. So 0.379 7 to 9. So then I should write this as 1. Summation of all these membership rate must be 1 only. So once again, I mean to say that once I'm writing 0.4, that means where membership grade is more, that means that item is much more closer to that cluster. When membership grade is less, that item is little bit far from that particular cluster. But again, there is a possibility that item may belongs to some cluster. So by this manner, we solve that particular case, that overlapping case, that when a particular data point may belongs to multiple number of cluster actually. So whatever things I am writing, value 0.4, 0.32, 0.1, all I am telling membership grades, degree of membership. What does it mean? So this is the involvement. I can say this is the involvement or this is the contribution of that item in that particular cluster. Okay, so here I have written usual that constant sum of weights of each individual item should be 1. Here weight means I mean to say, so this is the membership rate. Sum of membership rate of this individual item should be 1. Now another question may be there, okay, then how this fuzzy clustering we can convert it to partitional clustering? How this fuzzy clustering can be converted into this partitional clustering? As you know, this in partitional clustering, each and every item belongs to one cluster. So I think you can think about it that how this fuzzy clustering we can convert to some partitional clustering. Here simply a fact is like that, you know, that for one item, as I was telling, that multiple membership grades may be there based on the different clusters. So where you will find out that, okay, for this item, suppose I am telling for whatever I have given this item in the figure, whatever I am showing this item A, so this 0.4 to this cluster membership grade is more. That means possibility of assigning data point to A to that cluster where membership grade is 0.4. Right now where I am circling it is more. That means we will assign this data point to this cluster. So this is one way that we can, this is not the right thing actually, this is should not do that, but anyway, this is one way that we can assign data item to the clusters which is in which membership degree will be highest. Okay. Now another type of clustering, that is hierarchical clustering. You know, hierarchical clustering means hierarchy. If you see, if you know that what is hierarchy. So if I draw the hierarchy of NITW Warangal, of hierarchy of any institute, then what will be top? Maybe that board of governors, then maybe directors or maybe administration, maybe all the deans will come under picture, then all the head of the departments, under the head of the departments, various faculty members will be there. Under various faculty members, various students will be there. Now, see, this is a hierarchy. Now, so what is hierarchical clustering? Okay, so here, what actually two types of hierarchical clusterings are there, or slowly we'll discuss this. So here, see that one larger cluster can contain smaller clusters. One larger cluster can contain some smaller clusters also. But what is an example? Let us see. I want to say that NITW Warangal. Okay, if a larger cluster, then what are the various clusters? Various department, maybe computer science and engineering, maybe electronics communication, maybe electrical, mechanical. So all this belongs to NITW Warangal. And see, if I say that larger cluster is CSE department, then under CSE department, you know, artificial intelligence, data science branch is there. It is MCA branch is there. Okay, BTech, MTech, all these things are there. So all these are smaller clusters. So hierarchical clusters means here one larger cluster may contain some smaller cluster also. Often we can organize as a tree dendrogram. So as I was telling, so if this is the root, so this is our director, then from director it may be some dean will come. Again, then again we may divide it now. From here again we can divide, okay, different departments head will come here. Under the different department heads, again different faculty member will come. Under various faculty members, again, the number of students will come. So all these things, that means that we can maintain some hierarchy here. Okay. Now let us see. Hierarchical clusterings we can divide in two types. One is bottom-up, second one is top-down. So bottom-up means it is agglomerative clustering. Top-down means it is divisive clustering. In bottom-up, what you will do? So here you will start considering each data point initially a single cluster. So tree. So if I draw that tree bottom up, then what will happen? So suppose this is my tree. Okay, let us say this is my binary tree. So here each and every leaf node, so it is a cluster. Okay. Now if we can combine these two clusters, then what will happen? See. So here each and every data point, each and every leaf node, we are considering one cluster. Okay. Now if similarity is high, that means if these two leaf nodes belongs to CSE department professors, then obviously we can combine them under CSE department. If similarity is high, then we can combine all these leaf nodes actually. How much time I can combine? Until unless we can move to a single cluster. Now what is divisive clustering? So this is again different thing. So we'll start with root or single cluster, and then slowly we'll try to divide into some sub-clusters. So again, similarly, so if we come to CSE department, as I was telling, that then under CSE department we will find out, okay, MTech sessions are also there. Yes, BTech is also there. MCA is also there. So that means easily we can divide the CSE branch into this MTech, CSIS, MTech, CSE, MCA, BTech, all these clusters easily we can divide. Okay, now this is the algorithm that we'll avoid. So this is some measures actually. So I'll ignore it, that how we can find out this proximity or similarity measures between the clusters. We'll come to another type of clustering, complete and partial clusters. You know, whatever the algorithm today we are going to discuss, k-means clustering or fuzzy c-means, all belongs to this complete. Complete cluster means what? Complete cluster means each and every item to one or more number of clusters you need to assemble. Just 1 minute. हेलो हाँ हाँ बोलिए हाँ ठीक है एक्चुअली मैं मीटिंग में हूँ ठीक कल बात करता हूँ आपके साथ ठीक हाँ so complete and partial clustering, you know, what will be complete and partial clustering? Now let us see. As I told, that complete clustering means each and every item must belong to one or multiple number of clusters. That means there should be no item, okay, that which is not belonging to any clusters. Now what is a partial clustering? Here, partial clustering may not assign some data items to any cluster. You know, some outliers may be there, where the items that are not sufficiently similar to any other data items. Outliers may be a perfect example for this. But in complete clustering, each and every data items must be assigned to some clusters. There will be no data item or no object left, which is not assigned to anyone. But in case of partial, again, some data items may be there, which may not be assigned to any of the any of the clustering segments. So what about k-means or fuzzy c-means we will discuss today? Obviously, those will belong to this complete clustering. Again, some kind of clusterings may be there. It is prototype-based clustering. Okay. So now what is prototype-based clustering? See, prototype-based clustering. Here that means each cluster is defined by a prototype. Prototype means what? Prototype means here it is centroids. Centroid means what? Centroid means this is the cluster center. What do you mean by cluster center? Obviously, which is the most representative point in that particular cluster. That means using that point, you can represent your cluster. So this is called prototype-based cluster. So whatever today you are going to discuss, k-means clustering, so that belongs to this prototype-based clustering. That means here, once we will consider a cluster, obviously same time we will consider a cluster center. Cluster center is nothing but the centroid. So as I was telling, that cluster is a similar a cluster is the set of items in which each item is closer to the prototype. That means in a cluster, each and every item should be very much closer to the centroid or cluster center in comparison with any other data points. When you will feel that this set of data points belongs to this cluster, obviously, if we find out the distance of all those points is very much less from the cluster center, that means distance is less means in the another sense, similarity is more with those data points to this cluster center, then probably this is the right choice that, okay, you can put those items into this cluster center actually. So k-means clustering is one example of this prototype-based clustering. So another thing is that density-based clustering. So I am avoiding actually what is density-based clustering. So here maybe similar type of items will be much closer to each other. So let us avoid this. Okay. Now another kind of clustering, it may be graph-based clustering. So in graph-based clustering, what you are doing? So in graph-based clustering, you know, it is since it is graph, that means you can say that whatever our data points or objects you are considering, if you consider those as the vertices, then there will be a connection. There will be an edges. Okay, which vertices are similar, which data points are similar, you need to put some edges to connect them. Okay, so that assume the items represented is a graph in which items are nodes and similar items are linked by edges. So this is the most important point for this graph-based clustering. We are considering items as the nodes. And once you are thinking, okay, those items are similar, then obviously those items we need to link with some edges. Okay, so here a cluster is a group of nodes having more or better connections among obviously its members, then between its members and the rest of the network. So simply graph-based clustering, which are the similar data items, we will consider those as nodes and we will be linking them using these edges. Now let us slowly move towards our k-means clustering. Yeah. So now I feel that now you got the background for these different types of clustering and what is the objective of clustering, what is the purpose of clustering, as well as the applications of clustering, what might be the various type of clustering. So now maybe this is the right time to proceed with this k-means clustering. K-means clustering, see, it is self-explanatory only. K-means, that means how many cluster you will do here. You will do here K cluster. K number of cluster only you need to do. As I told that in clustering, one of the main difficulty is that predefined number of clusters. See, whatever the data set you are going to provide, unlabeled data set that I don't know. But again, I want to conclude that I will divide your data set, whatever you are giving, into k number of ways. That means into k number of clusters. Sometimes how it may be possible. It may be very much difficult. But again, k-means clustering has a very much significance in the scientific process. So here k means we are providing a fixed number, k may k, if I feel k is 3, that means obviously we divide the data set into 3 clusters. Okay, so needless to say that already I told that the fundamental ideas behind this clustering, obviously here you will see that all these points are grouped together. All this is one cluster, this is another cluster, and all these points belongs to another cluster. Now you may be surprising, wondering that how we are grouping actually that these items into one cluster. So that is the mechanism actually for this k-means clustering. So once we proceed through k-means clustering, then obviously that context will be very much clear. And k-means clustering also that belongs to the category of unsupervised learning, as I mentioned earlier. So we are working with some raw data, obviously, where label is not there. Okay, now k-means clustering. So how we are working with this k-means clustering? As you can remember, I told k-means clustering belongs to this prototype-based clustering. That means in the context of k-means clustering, we will apply the concept of cluster center or centroids. That means we'll assume that each and every cluster will have some centers, cluster centers. Now you may ask me, sir, what will be the cluster center? Is it a new point, or whatever the objects or whatever the points you are considering, you will take one point as a cluster center? Now both may be correct. So you can define your own cluster center as well as from the set of points randomly you can pick up some point as a cluster center. So both things are correct. So let us assume. So that means, so let us assume this is your cluster center. Let us assume, or this is your cluster center. This set of point, this is our cluster center. Then obviously, if you find the distance of these data points from this cluster center, and if you take summation of the distance, definitely it is going to be less on. The switch on the fan. One first. Take you. Yeah, so as I was mentioning that now the main problem is that how to define these cluster centers. I told you two ways actually. So you can consider that whatever the points you have, out of them one point you can consider a separate point. Now, how automatically the cluster center is coming in the middle, so that once cluster center is coming in the middle of these clusters, only then that our mean distance of all that particular points from that cluster will be less. But how automatically it is coming to the center actually? So some specific mechanism is there. So once we'll proceed, I think the concept will be very clear. Now see, so this is the algorithm for this k-means clustering. So maybe this is the mainly two steps we follow. Initialize k random points as cluster centers. Now see, here, whatever the objects points you are providing, so irrespective of that, we are initializing, since it is a k-means clustering, that means initializing k random points as these cluster centers. K random point we are initializing as cluster centers. Now see, assign data points. So then what you need to find out? You need to find the distance of each and every data point from those cluster centers. I'll show you the example. We have some graphical example, then things will be very much pretty clear. What I am telling, suppose our k value is 2. The k value is 2. And we have, suppose I am telling k equal to 2, and whatever the data points we are having, that is 10. That means from each of the 10 data points, you need to find that distance from these two centers. K equal to 2. I have considered two centers. Let us say one is A, one is B. That means for each of the data points, you need to find out that distance from A as well as B. Then what you will do? Then where distance will be minimum, you will assign the data points to that cluster center only. So that is the crucial thing behind this k-means clustering. Assign data points to the closures cluster center by measuring with a specific distance value. What I told. For each and every data point, you need to find out the distance from these two centers. So suppose one data point is closer to A in comparison with B, then assign to it cluster A. Suppose second data point is closer to B in comparison with A, then assign to cluster B. So this is the same. Assign data points to the closest cluster. Next, what will happen? So next we need to update the cluster centers. How to update the cluster centers? You need to take the mean of various objects, whatever you have kept in that cluster. Okay, what will be the mean value? That will be your new cluster centers. That's why assign the center of the cluster to the average of the points assigned to it. That means see here. So now I have changed my cluster centers. Suppose right now my cluster center are A1 and B1. Again, I should repeat the same process. From all the points, I need to find out the distance from A1. I need to find out the distance from B1. Which is less, I need to keep under that cluster. Again, once clustering is done, I need to find out mean of all data points which belongs to A1, mean of all data points which belongs to B1. And what will be the mean value? That will be on new cluster center. See, slowly how I am updating, how I am changing the position of my cluster center. Now, obviously, at some time, it will come perfectly to the center position. And this is the fitness function for k-means clustering, that, as you know, that as I was telling, that we need to find out the goodness of your clustering process. Whatever clustering you have done, how to find out the goodness of this clustering. What is fitness function? So fitness function means it will measure the quality of the cluster, whatever you have implemented. So, most widely used, particularly MSE, that is mean square quantization error. So that is the most widely used this measures for this clustering technique. Now here I have shown you some fitness function. Just see what is the fitness function, how we can measure intra-cluster distance using the fitness function. See here, OB or object. Two things I have kept, OB or object, CB or cluster. Okay, so this L equivalent to 1 to K means number of cluster. L equivalent to 1 to K, here K means our number of cluster. OI belongs to CI. What is OI? OI means object, which belongs to this cluster CL. L means what? It may vary from 1 to K. See now, D, OICL. That means what it will do. Suppose initially L equal to 1. Initially L equal to 1. What is OI? Y means what are the various points, objects which belongs to this cluster 1. You find out the distance. Next, what you will do? Next, this L, it will be 2. It will be 2. Then what you will do? Then what are the various objects which belongs to cluster 2? That you need to find out the distance. You need to make the summations. See, that means in this manner, you have 3 clusters. That means you are getting, firstly, what are the summation of the distance which are belonging to cluster 1, which are summations of the distance of objects which are belonging to cluster 2, similarly to cluster 3, then you will find out the distance, total distance. And if here the total distance is less, that means you will find out intra-cluster distance is less, that means whatever the clustering you are doing, clustering is good only. Fitness function, now see here. How, once again, how we are finding the fitness function? We are finding the distance of each and every point from a cluster center. Cluster center 1, distance of all points which belongs to cluster center 1. Next, distance of all points which belongs to cluster center 2. Similarly, we are proceeding. We are finding the distance. Now here we have used Euclidean distance. So this is the way to find out Euclidean distance. Actually, number of distance measure are there, Euclidean distance, Hamming measure distance, number of things are there. But here, for the sake of simplicity, we have considered this Euclidean distance mechanism. Okay, now let us come to some example. Then we'll make it very clear. Let me come to some example first. Then the things, once again, we'll discuss the algorithm. Okay, so let me come to this example. So here, suppose we are providing this input. Okay, this, what are the figure? So this input we are providing. Now I am asking it to do the clustering. Okay, this is simply our data set we are providing. We are asking to do the clustering. So how we'll implement clustering here? Let us check it here. So again, better I should say that here we will apply k-means clustering where the value of k is 2. Then what we will do? See. So firstly, we will randomly initialize 2 or more points. So we have 2 points only since k means 2. So call this cluster centroid or center of the clusters. Okay, as I have written, if you want to cluster, then you will choose 2. That means here 2 means k equal to 2. Okay, that means 2 cluster center we are considering, where initially we are considering the cluster center randomly, initializing these 2 cluster center randomly. Then what you will do next? Next, from each and every point, we need to find out the distance. From this point, distance of this. From this point, distance of this point, distance of this. What I am finding? Distance of this point right now, wherever I am marking, to this symbol, whatever right now I am marking is less. That means this data point may be belonging, you can assign to this cluster. Again, go to the second data point, this data point. Again, we assign, find out distance from this point as well as distance from this point. Where the distance is less, assign the data point to that particular cluster. Okay. So if we proceed with that, then see this figure right now where I am highlighting. So here we will find out this red point actually, it belongs to this red cross, this particular symbol. And all this particular green, blue, so that will be belonging to this. So how I have done it? So nothing is there, based on the distance measurements only I have done it. Where distance is less, simply I have assigned the data point to that particular cluster. Okay, now let us see. Now see here. Here we are finding, okay, this is our cluster center. Now see magically how this cluster center will change their position. See my next figure, check. Cluster center are changing their position. I am surprising that how this cluster center are changing their position. So to do it, what we need to do? So here we will take the mean of all the red dots. Whatever the red dots we have taken, red dot means what? It belongs to my this cluster, red cluster, and this other dots belongs to this blue cluster. That means whatever the red dots are there, if we take mean of all those red dots, then you will get some value. And move your red centroid to that value. What I mean to say, take the mean value of all the points which belongs to your red cluster, and then you shift your cluster position, whatever you take initially from random to that particular mean value position. So here exactly that we have done here. Similarly, we have done for this blue centroid. We have taken the mean value of these blue data points and then we have relocated the cluster centers accordingly. Now see here. So how cluster center is moving. So how cluster center is slowly moving. So each and every step. So suppose this is done, then what we will do? Let me just clear it. This process is done. Then what we will do? Cluster center has moved. Then again, you need to find out the distance. Again, repeat the same process. From this point, find the distance. If you feel this point is closer to this, assign to this. Again, this point, find out the distance. From both cluster center, if you feel this point is closer to this, then assign to here. So that means these two steps you need to repeat in each and every iteration. Okay. Now see here how the cluster center are changing their positions as well as cluster points also. So sometimes red clusters, they are getting more number of points from blue clusters. Blue clusters also taking some point from the red clusters. Now see, since cluster center is changing, obviously the objects, how many it was earlier, what are the objects, the content earlier, that objects also will be changed. Now see, slowly how it is coming to the center point. So simply we are considering the mean values of those data points, so which belongs to red cluster or which belongs to this blue cluster. Obviously, by this mechanism, these centers are slowly relocating to these centers, to that particular cluster centers. Now see here. So if you continue these few iterations, now you will find out these cluster centers are exactly middle. So that means this is one cluster and this is my second cluster. Now see here. So how importantly initially started with a random cluster centers, and based on this K-means clustering mechanism, how these cluster centers took the right place, and we got these two clusters actually. So here some graphical examples I'm trying to show. Now see initially where the cluster centers we have kept and how those cluster centers are changing their position actually. And then we are getting two clusters. And here also, so see that here whatever we have assumed, so instead of two cluster center, we have now three cluster centers. Here K means clustering we are applying, but here value of K we are assuming 3. Now see that how all these points are changing their position. Initially, we set their positions randomly, but once we are proceeding through the iterations or mechanisms of K means clustering, then how slowly all these points are changing their position. Now here see, so here how this cluster center is coming to the middle. Initially it was some random point, but how it is changing their positions actually. So all these mechanisms are there. Now each time we are computing the mean, obviously once we will computing the mean, it will help us to relocate the cluster centers directly at the middle point of this. Now I will explain this algorithm, then it will be very clear. This is our K-means clustering algorithm. So choose these K random data points as seeds to be the initial centroids. Whatever you have seen in these graphical examples, we are selecting K random data points as the initial centroids of these cluster centers. Then see, assign each data point to the closest centroids. See, assign each data point to the closest centroids here. So this cluster Ci, which data points will assign? Just check. If xj, so you are finding the distance, this we are finding the distance. Okay. So where distance is less, only that position only, this j, that means we'll assign to Ci only. Where distance is less actually, we'll assign to Cj. Now what is μi? Here I mean to say these are the cluster centers actually. This IL, this belongs to our cluster centers. So this is what is xj. X means this is our data objects. Okay, so which is mathematically I am representing that how to find out which data belongs to which cluster. Then what you need to do? Recompute the centroids using the current cluster memberships. We need to recompute the centroids. That means you need to take the mean value of all these data points, and ultimately you will get the new position for your cluster centers. So I'll give you some numerical example, then it will be much more clear. Now see this numerical example for this K-means clustering. Now see here, look here very carefully. So how many data points we have considered? 1, 2, 3, 4, 5, 6, 7, 8. So 8 data points we have considered here. Okay, so this is your data points. A1 means 2, 10, A2 means this, A3 means this. So these are our data points. Okay, fine. So what is your initial centroids? So here we have not considered randomly any other centroids. Based on the given data points only, we have assumed our centroids. Okay. So what is your initial centroids? This A1, B1, C1. So all these things we are thinking as our initial centroids. Okay. So that means A1, I took this A1 initial centroids, B1 initial centroids, and C1. So maybe here K means algorithm and K is 3 actually. Now what you need to do? Look very closely. So this is our cluster center 1, this is your cluster center 2, this is your cluster center 3. So what I am doing? From each and every point 2, 10, this is my 1 point A1, I am finding the distance of cluster center 1, cluster center 2, cluster center 3. Now what will be the distance of cluster center 1 from this of A1? Oh, it is 0 only now, because it is 210, it is here also 210. Now this is your distance mechanism. So here I have written it. So this is my distance mechanism, whatever I am applying here. Apply that from 210 to 58. What will be the distance? If we apply this formula, we will find out the distance will be 3.61. Simply 210 to 12. What will be the distance? If we apply this formula, distance will be 8.06. Now see, so from A1, now we have computed the distance from these 3 cluster centers. Now to which cluster you will assign? Where distance is minimum. So you are assigning it to cluster 1. So little bit I'll make it clear, so to have proper understanding on it. Okay. Next, we will repeat the same process for A2, 2, 5. So for A2, first find out the distance from 210. So this is my equation or expression, whatever you can use to compute this distance. This is d of P1 by P2 right now, wherever I'm highlighting. So this is my distance mechanism procedure. So A2, 25 to 210. If we apply this, distance will be this. See, so for this point A2, we are defining the distance from all 3 cluster centers. That is very important. 25, 210, 25 with this 5 8. Cluster point 2, cluster center 2, here it is 4.2. Then this A2, we are finding the distance with this point. It is 3.16. So where distance is minimum, easily we can find out that in cluster 3, this is our cluster 1, this is our cluster 2, this is our cluster 3. So here in cluster 3, distance is minimum. That means we'll assign it to cluster 3. So the remaining data points, we are doing the same thing and we are getting the value. We are assigning this in the corresponding clusters. So not repeating for all every data object, say 3, B1, B2, B3, C1, C2, I am maintaining the same process, following the same thing what I did for first 2 data objects. So now see here, for each and every data points, I am getting some cluster. Each and every data points, I am getting some cluster here. Okay, up to this point, it is fine. Next, what I should do? Okay, some clusters, I have got it. That means which data point may belongs to which cluster. Up to this point, it is very much clear for me. Which data point may belongs to which cluster. So next, what I should do actually? Next, I think, so what we need to reassign, we need to relocate our cluster centers. So initially, we started with these cluster centers. First phase is over. Second phase of my first iteration, we need to relocate the cluster centers. How to relocate? We need to compute the mean of those data items which belongs to the same cluster. Let us see. Let us check it. So how we will calculate this? Let us see here. So this one, let us consider one, cluster number one. So which data points belongs to my cluster number one? This is my cluster number one. This 210 belongs to my cluster number one. Only one thing, only one data point is that 210 belongs to my cluster number one. That means obviously one of the center will be 210. Now let us assume, let us think that which data points belongs to cluster number three. So this 25 belongs to cluster number 3 and 12 belongs to cluster number 3. Then we need to take the mean. That means 2 plus 1, 2 plus 1 by 2, 3 by 2, 1.5. 5 plus 2 by 2, 7 by 2, 3.5. So 1.5 and 3.5, that will be our new cluster center. Just check. For C1, 1.5 and 3.5, that is our new cluster centers. One is A1, 210. Second one is this. How to compute this? 6, 6, how it is coming? See, 2. This is 2. This point belongs to 2. This is 2. This point belongs to 2. This point belongs to 2. This as well as this. Now compute it. So that means 8 plus 5, 13 plus 7, 20, 26, 30. So 30 by 1, 2, 3, 4, 5. 30 by 5, that is 6. So that's why this value is becoming 6. Similarly, the other value also will come. So now are you getting that how computing the mean value, we are reallocating the centroids? Okay, up to this part is over. That means we are getting new cluster centers. Then what you need to do in the next phase? First iteration is over. In second iteration, so we need to repeat the similar process. Now see here. So this is our new cluster centers. So here updated the cluster centers actually. Updated the cluster centers. So you need to repeat the same procedure. That means for each and every data points, now you need to compute the distance from this cluster center. From each and every data point, you need to compute the distance from each and every cluster center actually. Once again. So let us see. So I'm not repeating. So if you define the distance from A1 to 210, obviously it will be 0. From A1 to 66, it will be this. From A1 to this, 1.5, 1.5, it will be this. This 3.5, I think. So it will be this, 6.52. That means which is minimum? Obviously, this 0 is minimum. That means you need to, this is your cluster 1, cluster 2, cluster 3. So obviously, you need to assign it to cluster 1. Similarly, for data point 2, if we do the distance, if we find the distance, then we will find here distance is minimum. That means we'll assign A2 to cluster 3. Similarly, we'll assign each and every data point to their corresponding clusters. We have assigned it. Now check. Should we stop here or we proceed more? What is the termination criteria for this k-means clustering algorithm? Can we terminate our process or we can proceed next? No, it is not terminated. We need to proceed. How to determine? Just take it here carefully. So here cluster center 1, 1, okay. 3, 3, okay. Okay, this 2, 2, okay. This okay. This is okay, okay. But here it is changing. So once cluster center is changing, that means there is no way to stop. You need to proceed. Okay, that means once again, we need to find out our new cluster points, new cluster centers. And you know that what is the mechanism to find out the new cluster centers. So based on the same thing, once again, we'll find out the new cluster centers we are finding. So right now, this is our new cluster centers. So similarly, we took the mean value, whatever we did earlier, not repeating that. Similarly, we are finding the new cluster centers. We got the new cluster centers. What is your next process? Again, to find out the distance of all these objects from these 3 cluster centers. Okay. So these are my 3 new cluster centers. Okay, this is my cluster 1, cluster 2, cluster 3. Again, you need to find out the distance of these objects, okay, from my new 3 cluster centers. Let us say from A1, what is the distance? 1.12. A1, what is the distance of this? 6.54. From A1, what is the distance of this? 6.5. Which is minimum one? So first one is minimum. Assign it to cluster 1. Similar process we need to implement for all others. Now you check what is happening here. Cluster center is changing, 1, 1, 3, 3, 2, 2. Again, cluster center is changing. So it is another difficult procedure. So cluster center is changing. That means again you need to repeat the similar procedure. Okay, let us repeat it. We are repeating the similar procedure. We are finding here new cluster centers. Again, you need to do the same thing. This is our new cluster center. We need to find the distance of all the data points from our new cluster centers. And you need to assign to them some new cluster. Now you check, cluster center is changing. This is 1, 1, 3, 3, 2, 2. No, cluster center is not changing. That means perhaps your k-means clustering algorithm has got the convergence, so you can convert it or you can terminate your k-means clustering algorithm here. So here you got the DGR cluster. So this is one of that, I think, numerical example behind this k-means clustering, how it is working. Now this is the flowchart for this k-means clustering algorithm. So once you have understood the example, I think easily you can understand this flowchart. So this is starting, this is number of clusters. We need to find out the centroids. We need to compute the distance between the item and centroid. We need to allocate them based on the minimum distance. Okay, then no new item move group. That means, okay, cluster center is not changing, then stop. Cluster center is changing, then okay. Again, you go for finding new centroids, go for finding distance, newly allocate the cluster centers. Again, you check cluster center is changing, no. Like that. So you need to repeat this process. Now let us come to another important scenario, that is fuzzy semi clustering. So quickly I will tell this fuzzy semi clustering or fundamental principle behind this fuzzy semi clustering. So this fuzzy semi clustering, so actually developed by Bezdek. So in 1981, again, this is a type of this unsupervised clustering only. As already I told some idea regarding these fuzzy sets, so it is based on the concept that more data is near to the cluster center, the more membership value of data will become part of that cluster. As I told earlier, that sometimes it may be very difficult to distinguish that one data point belongs to this cluster or that cluster. Then there will be a possibility that one data point may be belonging to multiple number of clusters. Where the degree of belongingness is more, then you can need to assign more membership value. Where degree of belongingness is less, there you need to assign less membership value. The main benefit of this fuzzy semi clustering is data point can have a degree of cluster membership. Cluster membership means what? How much it is belonging to the cluster. A data point, if comparatively it is near to the cluster 1 and comparatively far from cluster 2, so maybe cluster membership degree for cluster 1 may be 0.7, remaining may be 0.3. Now you may be asking me, sir, once you are finding that it is closer to cluster 2, it is closer to cluster 2, it is far more from cluster 1. Again, why you are not using that particular complete clustering actually? Why you are this partial clustering kind of things, why you want to implement? Here, what I mean to say that what is the need of this fuzzy k-means clustering? Sometimes no, you may not have sufficient information to compute that one particular data point is belonging to which cluster. You don't have sufficient information. Then what you will do? If you have sufficient information, then if your information belongs to the certain category, then it is okay, go for k-means clustering. But once if you have some uncertain kind of information, where information may be missing, imprecise, maybe incomplete, maybe nothing, all many things may be there, maybe distorted, then what you will do? Then there is no way now. One information is not there sufficient. Then how you can assign completely to another cluster? Then it's better that okay, it may belongs to that cluster with certain membership degree, it may belongs to the other cluster with certain membership degree, then this kind of situation will come. And we believe that fuzzy Siemens is very much popular rather than this k-means algorithm. Okay, but because fuzzy, whatever, when some problems are difficult to solve using k-means clustering, all those problems easily we can solve using fuzzy Siemens clustering. Now, this is the objective function I have given for this fuzzy C-means clustering. Now, see here. So earlier you have seen this distance measure was there for this K-means clustering. Here, what is this is our data object xj, and what is v? V means it is the cluster center actually. Cluster center, this is our object. Now see, here I have written assigning some membership value, mu ij. This is membership value actually. Now what is n? See, this is feature vectors. What is c? This is the number of clusters. Now see, that means, so here what I mean to say that once I am writing uij, that means my item j, how much it is belonging to this cluster j. So that particular thing I am denoting it mu ij, membership grade of item I to belong to this cluster j. That is depicted by this mu ij. Membership rate of this data point I, how much it is belonging to this cluster J, that I am identifying using mu ij. Now see important situations, that means in fuzzy C-means clustering, or normally what we will do. So normally for each and every data point, okay, for each and every data point we find out the fuzzy membership degree from each and every cluster point. See what I am telling. Simply K-means algorithm, what we do? We find out the distance of each and every item to the various cluster centers. In fuzzy C-means clustering, we find out the fuzzy membership degree, that means clustering membership degree of each and every item to each and every cluster. So similar manner we are doing here, and since we are working with this cluster membership degree, that's why here we are writing this mu ij. That means the ith item belongingness of ith item to this jth cluster. So if you know this concept of fuzzy membership degree of fuzzy sets much more clear, then probably you feel comfortable. Otherwise, right now it may be a little bit difficult, because this fuzzy set has its own definition actually. It has its own different characteristics. It is actually, it is a one important topic, so that we need to know. So then it may be, all these ideas may be very much clear for us. Now here more things I have kept. Now, as I told a few things, so now you know that let us so suppose this is our cluster center C1, this is our cluster center C2. Okay, let us see, these are some items are there, some items. So cluster center I'm denoting this symbol, and these circles, these points. So these are our items actually. That means, so these items may belongs to this cluster, these items may belongs to that cluster also, with some degree of belongingness or membership degree. Now, if this data point belonging to cluster C1 membership degree 0.3, then it must be 0.7. Actually, this is some rules of fuzzy set. So summation of this membership degree must be 1. Okay. So like that. So once that means it belongs to this point, or it may belongs to this point. It belonging degree of this point is 0.3. Then belonging degree of C2 it will be 0.7. So that must be 1 actually. So this is, now see here I have written for I equal to 1 to C, this mu ik, that must be 1. That means if I 1, that means in cluster C, okay, I 1 to C, that means cluster 1 to cluster 2, what is the membership value? Okay, that this kth object is belonging. So if we take the summations, so summations should be must be equal to 1. Otherwise, it will be incomplete sense of it. That means once we are telling, okay, the degree of belongingness to some cluster is 0.3, obviously degree of belongingness to some cluster should be some values, so that if we compute the total value should be 1 only. So regarding this fuzzy C-means clustering, we will not discuss in detail. So simply we will show the flowchart of this fuzzy C-means clustering, because to discuss this fuzzy C-means clustering, we should have a good knowledge of this fuzzy set. Otherwise, it is a little bit difficult to understand this fuzzy C-means clustering. So here I am trying to give you an overview of this fuzzy C-means clustering. Then quickly we'll move to some different things where we will show that how we can apply this clustering algorithm, as well as some optimization techniques to solve some problem, to solve some real life problem that we'll try to focus. So this is our flowchart for this fuzzy C-means clustering. Okay, now let me come to that particular problem here. What we will try to do, so quickly within 15 minutes, so I will show you, I will try to describe one optimization techniques, that is gravitational search algorithm. And then what I will do, I will combine this k-means clustering with this gravitational search algorithm to solve some real life problem. Then you will get to know that how clustering algorithm is helping us to solve some problem. And at the very beginning, you can remember that I told that clustering algorithm, sometimes we may use pre-processing for any other algorithm also. Here, this k-means clustering we are using, to generate the initial population of this gravitational search algorithm. You know that once gravitational search algorithm, it is one of the meta-heuristics algorithm, and once you are working with some meta-heuristics algorithm, then how you are computing the initial population, that is going to take a huge part in the computation once you be proceeding with your algorithm. If your initial population is not that much good, then sometimes your algorithm may not converge, or whatever the solution you will get, that may not be the good solutions. So contributions of this initial population is significant for any of the meta-heuristics algorithm. Here, whatever we have done actually using k-means clustering algorithm, we have formulated the some candidate solutions which will be applying as the initial population of this gravitational search meta-heuristics algorithm. So before proceeding with this gravitational search, let me give you a quick introduction on this gravitational search algorithm very quickly, so that you will understand the fundamental things. Then we'll try to combine these two logic to get some specific output. Name itself suggests it is gravitational search algorithm. Obviously, it may be related to gravitational search. So if you see this picture, law of gravity, so this is a Newtonian's law of gravity. So, in this universe, two particles are attracting each other. So how they are attracting each other? What will be the force, a gravitational force that they are attracting each other? See, if M1 and M2 be the two particles, okay, and R be the distance between these two particles, and G be the gravitational constant, this is nothing but a Newtonian's law of gravity only. How these two particles will attract each other? This is the gravitational force. So this is the equations G into M1 into M2 by R square. Here we are taking squared distance, that is R square. So this is the Newtonian's law of gravity. So exactly we will apply this concept in this gravitational search mechanism. And now, as you know that once we will apply some force on Newtonian's force on some particle, once we'll apply some force on some particle, so obviously that particle will start moving. It will get acceleration. So what will be the acceleration? That we may get from this Newtonian second law actually. When a force is applied to a particle, acceleration depends force and the mass. That means now see the situation here. Particles are there attracting each other with a gravitational force. That is creating a movement among the particles. Movement among the particles means, technically I should say, that particles are communicating with each other. Particles mean what? Particles means our object. Broad manner means the solutions. So solutions are communicating with each other, and ultimately when solutions are communicating with each other, that may lead to some better quality solutions in the later iterations. So here I have shown you that some actually expressions. Two things are there actually. One is active gravitational mass. Second one is passive gravitational mass. What is the active gravitational mass of I? So in how much force it is applying to J? That is active gravitational mass of I. And how much force J is sensing from I? That is called the passive gravitational mass for this object J. Okay, so these two definitions are there, but here to make our example simple, here we have assumed that active, passive, and inertia mass all values will be same only, similar only. What is inertia mass? Inertia mass means that much force is required to displace that particle. That is called inertia mass. Okay, now see here. So here, remember, whatever I am writing masses, so consider these all are about solutions only. See, here I have given 4 solutions. Now check it here. Mass of this solution M3 is more. You know, once I tell, mass means what? Mass means quality of the solution. Once mass is more, solution quality will be more. Once some solution quality is more, obviously, that solution will attract each other solution towards it actually. So what is happening? Just check it here. So this M4 attracting M1 in this force is F14, this M2 attracting M1, this force is F12, and this attracting force is 13. So if we take cumulative force may be this one, F1. That means what is happening? This M1, this particular solution slowly started moving towards another direction. Now, actually, you know the concept of search space. So, see, each and every solution are there in search space. You know, in search space, we have a number of solutions. So, we started with some random number of solutions. What is our objective? To find out the better quality solutions. Now, if a solution moves from this position to this position, that means what? This is another solution only now. So that means here, once solutions are moving to the search space, each and every move, we are exploring some new solutions. And that is helping us to find out the better quality solutions. Now, this is some working ideas regarding this gravitational search algorithm, as I told. That agents are considered as objects. Agents means nothing, these are the solutions, considered as objects. And their performance is measured by their masses, as I told earlier. Masses are more. That means obviously solutions is good quality solution. Mass is less, solution is poor quality solution. See, all the objects attract each other by this gravitational force. And obviously this force will lead to a global movement of all objects towards the heavier mass. Are you getting? Ultimately, our objective is that to move that particular solutions. If we can move the solution in the search space, then what will happen? In the process, in the longer run, we will reach toward desired solution. If there is no movement, no solution. Since that solutions or particles are moving, particles are nothing in the context of our program, we say it is a solution. Once each and every solutions are moving, obviously we are in a position to explore our search space in much more broader manner. And we are exploring each and every solution in the search space in order to get the better quality solutions. Now, see the important thing, what will happen? See, the heavier mass, obviously heavier mass means better solution, which correspond to good solutions move more slowly than the lighter ones. That will guarantee exploitation. As you know that each and every meta-heuristics algorithm, 2 things are there. One is the exploitation, second one is the exploration. You know, exploration means what? Exploration means diversity. Exploration means intensity, intensification. Exploration, diversification, exploitation, intensification. Diversification means what? Exploration. So initially, we'll try to explore the solution space as much as possible. That should be our objective. We want to explore the solution space as much as possible. That means we want movement of the particles as much as possible with the help of this gravitational force. Later on, what you want? Suppose I am moving to this solution. This is a heavier mass, means good solution. So once I'm closer to this solution, then what I will do? Slowly, I will reduce my exploration. I will focus on my intensification. That means what? That means once I am near to some good solution, so I will restrict myself. I will feel that it is a good solution. So which are the nearby solution that may be much more better one. That is the exploitation actually. Intensification. We are focusing on a solution. Restriction our movement on that one. So at any meta-heuristics algorithm, so there should be a proper balance between exploration and exploitation. And GSA is one such kind of algorithm actually very much famous only for that. It maintains a proper balance between this exploration and exploitation. Because see, it is what it is doing. So initially, it is what it is assuming. So initially, it is assuming some set of masses. Okay, and then it is actually what it is doing. It is creating movement of the masses. Now take it here. Heavier mass will not move that much. Lighter mass will move that much. That means heavier mass will go for this exploitation, and lighter masses will go for this exploration. Now see the situation. From this picture, it will be very much clear. So this is your object, means this is your solution. And these are the positions as well as this mass value. Now check it here. What is happening? So once you are moving, what is happening? Just check. Heavier mass, movement is less. But for all other mass, what is movement? Once mass is less, movement will be more. Mass is heavy, movement will be very less here. So position means obviously that is our solution, and mass value means this is our fitness value. So that are all the cases. Now quickly we'll come to some part that where we want to relate this, our K-means clustering as well as gravitational search algorithm. You know, this is our GSA. So simply flowchart, we need to create the initial solution, fitness for each and every agent mean solution, update G, best and worst solution for each and every population. We need to calculate mass and acceleration for each and every agent. We need to update velocity and position. I think maybe it is getting difficult. Now let me move forward, then it will be very much clear for you. Now see here. So here what we have. So we have some set of solutions. For each and every solutions, we are finding the fitness value. Fitness value means what? So these are the masses of those solutions. Now see here. How to calculate the mass in the context of GSA? Initially, you need to find the initial solution and then you need to compute their masses. How to compute their masses? See the expression. Fitness of the ith solution in one, this is in case of one iteration. Okay. Suppose this is one iteration or this is one population. So fitness of some solution minus worst fitness value. Base fitness value minus worst fitness value. So once you are in a particular population, obviously you will get which fitness value is the worst for that population, which fitness value is the best for that population, and particularly now also that which solution you are dealing with. Which solution you are dealing with, that is fitness I. And this is the worst, best, and worst. And this way, actually, we find the mass of each and every solution. See, QIT, summation of this J equal to 1 to N UJT. So as I told initially, once we are getting some solution, first target is to find the fitness value. Here we have seen, we are formulating the initial population. So our first target is to find out the fitness value. So this is the way actually we are finding the fitness value for each and every population. So these are some expressions. Here I have given that how to find out best and worst fitness value for the population. Obviously, it will be different for maximization and minimization problem. Now let us slowly come to that part that we see this is the force, how the force is getting applied. Okay, how we can compute the force. So this is the position, D with the dimension, and M, what this the masses of each and every, and this R with the distance. And we have just the smallest amount epsilon we have added. You know why we have added? So to avoid divided by zero problem technically, so that we have added this small value. So ultimately what we will do, just check it, what we are trying to do. So once we have computed the mass, then we are trying to compute the force. That means each and every solution, how much force it is applying to other solutions. So solution I, how much force it will apply to the other solutions, how we get. Solution I, how much force it is applying to other solutions. So D, nothing but the dimension of this problem. So here we have added a random numbers, because since all the meta-heuristics algorithms are stochastic in nature, So to incorporate the stochastic nature, we have included this random number because it will help us to come out from the local optima also. So we should not be that much bias. That means sometimes, so if solution mass is less, again that time our attractive force may be more. So some randomness we need to include each and every metastatics algorithm to come out from the concept of this local optima. So here we are finding the force. So based on the force, what will happen? So based on the force, acceleration, that means each and every solution will started moving. So acceleration will be there for each and every object. So if each and every object started moving. So once they will start moving, their velocity will be changed. So this is the expression that how to compute the velocity. Again, we have to use some random number, as I was telling, that for each and every materialistics algorithm, since by default stochastic in nature, so randomness we need to add each and every case. So this is your previous velocity, this is your X-ray acceleration, and we will get the updated velocity. Now see, from fitness value, we got the force. From the force, we are getting the acceleration. From the acceleration, we are getting the velocity. From the velocity, we will get position change. So see, based on the velocity, now each and every solutions are changing their position. This is the initial position. This is the current velocity. Obviously, that solution changed their position. What does it mean? Solution changing their position means you are getting a new solution actually. Solution changing their position, technically what it is, we are getting a new solution. Okay. Now, slowly here we will come to the close end part. So here I will show you that how now simplest sense I have told the working principle of gravitational search. Actually, it is a huge importance algorithm. But I hope that the fundamental ideas behind gravitational search you have understood. Now let us see that how we can combine this k-means clustering and gravitational search to solve some problem. What I told, k-means clustering I have applied to generate some set of initial solutions only. As I told you earlier, initial solutions for any meta-heuristics algorithm play a very crucial role once you are going to have a convergence. So here our main motivation behind applying this k-means clustering is that we are actually we are generating some set of initial solutions using this k-means clustering. So as I told, if initial solutions are better, then probably the working of your meta-heuristics algorithm also will be better. So this is the algorithmic approach actually where we have used this k-means clustering and some other means to generate the initial solution. Now, simply k-means clustering we have used to generate the initial solution. Then we have left it to GSA algorithm, gravitational search algorithm. So our algorithm consists of two things: initial phase, k-means clustering, and later phase, gravitational search algorithm. Where the contribution of k-means clustering only to generate initial populations. Now see here how we have applied our proposed algorithm to some real-life data set. This is a very much real-life benchmark data set actually. So you can get access this data set. So here 5 real data sets consider this iris, wine class, breast cancer, urine cancer, all this. So now see. So here whatever we are considering. So this n, this is the number of data objects, okay, and this is the number of features. K means the number of clusters. So these are the clusters. These are the data sets we have considered, and we applied our own algorithm as well as these other existing algorithms. See, this is the iris, wine, all these data sets are there. This is k-means, gravitational, this is genetic algorithm, simulated annealing. This is ant colony optimization. This is honeybee algorithm. This is particle swarm. This is gravitational search, and this is the proposal one, k-means based gravitational search algorithm. So what this table is showing, just if you look closely, it will show you the intra-cluster distance. What is our objective for any clustering? To minimize the intra-cluster distance. Now just to see what is the intra-cluster distance for all others and what is the intra-cluster distance for us. So what is our target? To minimize the intra-cluster distance. So that was our target, and we have seen that if we apply all this algorithm, obviously your proposal, that means which is a hybridization of k-means and gravitational search algorithm, so that will minimize this intra-cluster distance. Now let us come to some conclusion. So what is our conclusion? So obviously that once we want to apply the benefits of this two well-known algorithm, one is this k-means clustering, second one is the gravitational search. K-means clustering is very much simple and very much effective actually. Although here number of clusters are prefixed, but it is very much simple, widely applicable, as well as I should say it is very much efficient. So simply we are applying benefits of two well-known algorithms, k-means clustering, gravitational search algorithm, and we are applying it to some well-known benchmark data sets where we are finding that this combination of this hybrid method actually showing better performance. Now here actually I want to, since 2-3 minutes time we have, so I want to highlight in one more part, in particularly this gravitational search algorithm. Now see, here what should be our technique for this gravitational search algorithm? So technique should be that initially we will assume that we have, suppose, 20 number of high volume. Initially you need to consider, let us assume 20 number of that, what we should say, that high mass solution. High mass means better solutions. So the solutions having high mass. Initially, suppose it is K. Let us assume K. What is K? K means your number of solutions in the initial population. If your initial population number of solution is 20, then initially your K value will be 20. Then what should be your approach? Slowly, you need to reduce the K value. Just see the situation. Once I am proceeding, slowly I am reducing the K value. And you will be wondering to know that how to reduce the K value slowly during your proceedings throughout the algorithm. A number of research papers are there. Few research papers are telling that if you change the value of K linearly, you will get some set of result. Few research papers are telling if you change the value of K non-linearly, results will be much more effective. Now see the interesting situation. We are starting with a value of K, where K is nothing but the number of solutions in your initial population. And once you are proceeding through the generations, I am telling you reduce K. Sometimes you may reduce linearly, sometimes you may reduce non-linearly. But researchers are claiming that if you reduce non-linearly, maybe using some chaos theory mechanism or using some other mechanism, then probability of getting much more better solution will be higher with respect to the linearity. Now see, so that's simple how we can have some very good solutions, or we can have some effective solutions by simply changing a one variable, or the variable is K. We can change its linear manner, we can change it non-linear manner. So like that, so actually opportunity is there that once we are finding some variables, maybe k-means clustering, gravitational search. If you look closely, if you want to apply some thoughts on these things, then maybe that whatever solutions you will get, that may be much more optimum solutions. Okay, so that I told our research ideas, like that many research ideas may be existing. So recently we have done some work on applying gravitational search for the image segmentation also. You will find out huge application of these meta-heuristics algorithms are there in the context of image segmentation also. That means now you may feel free to apply the concept of k-means clustering as well as combination of GSA for this image segmentation. Probably you may get some wonderful result. Now, this is my references. Now, once again, thanks to the participants to listen me for this almost 2 hours. Now, the session is open for question and answers. Now, if you have any quick questions, obviously, I am ready to take. Participants may be feeling tired. They are attending sessions from 3 o'clock. So I'll not tell anything more. So please note down my email ID as well as contact number. So as I told in the last session also, please feel free to communicate with me if you want to carry out some good research works in this particular domain, or mainly domain of AI, as I told, machine learning and multi-criteria decision making, or maybe evolutionary computations or uncertain decision making. So again, if you have some questions, so please feel free to contact me in these numbers. Obviously, I will reply you back. So with this, now I will stop my presentations. I will check that if you have some quick questions, then obviously I'm ready to take. Let me check the chat box. I feel that participants are very tired. Actually, maybe they will ask me questions. Maybe they will email me or they will WhatsApp me anyway. So yeah, Professor Jagannath sir. So that's all about from my side. So one second.
Yes, sir. Thank you so much for your wonderful lecture, sir.
Yeah. So thanks. So once again,
Participants, any other questions?
yeah. So once again, since
Okay, so,
yeah. So since there is no other question, so now we'll close it. So once again, I would like to take this opportunity to convey my thanks, sincere thanks to these coordinators of this FDP, Professor Jagannath Rai from NITW Warangal, as well as Professor T. Ramesh Babu from SR University Warangal, so for their kind invitation to share my thoughts on this platform. And finally, also I want to convey my thanks to the participants, so for their patience to listen me. I believe at least they will get some ideas, whatever they can apply for their near I think research works. So once again, I want to thanks everyone. And then with the permission of the coordinators from NITW Warangal, Professor Jagannath Rai, so I leave the session.
Thank you, sir. Thank you for agreeing our invitation to share your knowledge and for wonderful 2 sessions. And I'm sure our participants has got a lot of information, lot of knowledge. And definitely they will try to contact you through email or phone, maybe to solve their problems. Maybe they will try to collaborate with you. And thank you, sir. Again, thank you all the participants. So yeah, that's all.